Hello, ladies and gentlemen. I'm here on behalf of the authors from the Warsaw and Rzeszów University of Technology, and I would like to give this presentation. Uniform rolled I-section beam column, laterally and torsionally unrestrained between endpoints, are commonly used in steel skeletal structures, for example, portal and multi-story frames. In Eurocode 3, we have two options for design procedures of steel I-section beam columns. The first, the indirect method, is based on the verification resistance criteria, where the interaction factors can be calculated according to method 1, which is more accurate but also more complicated for hand calculations, or method 2, which is more suitable for quick resistance verification. And the second, the direct method, in which all the stability and imperfection effects are included in one analysis that combines an advanced structural analysis and the verification of failure criterion referred to the whole structural system. The paper deals with an experimental study on the buckling resistance of rolled I-section beam columns under moment gradient and full-scale tests. Figure shows the subframe specimen installed for testing. The experimental program covered different stability phenomena, flexural minor axis buckling of columns and under uniform compression, lateral torsional buckling under triangular first-order major axis bending, and flexural-torsional buckling under interaction of bending moment and uniform compressive force. All specimens were constructed as an angle subframe of the same geometry. Figure shows details of the load application, namely the actuator applying to the force at the point A in order to produce the axial force in step 1 of the loading history, and the actuator applying the force at point C to produce the bending moment in step 2 of the load history. It is important to notice that the force produced by actuator at point C is resisted by the joint support at point B, so that this force does not affect the membrane compressive state in the beam column AB, the state being entirely controlled by the force applied at point A. Here, figure shows the placements of different sensors on the tested specimens and details of the placement of the sensors within the cross-section located along the member. Within the experimental program, some complementary tests were also carried out in order to confirm the steel grade of supplied products. So coupon tensile test for section flanges and the web were conducted to confirm the real section geometry of section walls, namely thickness and linear dimensions with reference to their nominal values, and to check geometrical imperfections. In this case, material imperfections were not measured. There were tested 6 cases of loading: compression without bending, it is test 1A, bending without compression, test 1B, and 4 different interactions of bending and compression. 4 subframe specimens were tested. 2 of them, numbered 1 and 2, tested twice. Now I show you 3 short movies of exemplary tests. The first one shows the test in the case of pure compression and the flexural minor axis buckling of the member. The second presents the test in the case of pure bending and the lateral torsional buckling under triangular first order major axis bending. And the last one shows the flexural-torsional buckling under interaction of bending moment and uniform compressive force. Okay. Here, figures show the deformation states in 2 load cases, compression without bending and bending without compression. It is clearly visible that in the compression test, the deformation state is almost entirely controlled by lateral displacements, while in the bending test, the deformation state is controlled by both lateral displacements and twist rotation. At the end, figures present the comparison of experimental results and results from Eurocode's interaction equations according to method 1 and 2, where the lateral torsional buckling reduction factor was calculated according to the so-called general approach and according to the special approach for rolled bisymmetric eye sections. Instead of the nominal value of yield strength, the mean value is taken for comparison of the results. We can see that Eurocode's analytical results obtained with use the so-called general approach to calculate lateral torsional buckling reduction factor are much more conservative than those obtained with the use special approach. And practically all results from Eurocode's interaction equations are below experimental results. So, this paper presents experimental investigations into the behavior of unrestrained steel beam columns of uniform rolled eye section. The novelty of experimental work is that the beam column is tested as the element of subframe specimens composed of cantilever beam and column rigidly connected to it through the bolted beam to column and plate joint. There were tested 6 cases of loading, compression without bending, bending without compression, and 4 different interactions of bending and compression. The great advantage of the tested substructure is the possibility to give any desirable proportion between the compressive force and the maximum bending moment, since they may be controlled independently of each other. Most of past and present experimental investigations of the behavior of beam columns were based on eccentrically compressed members where the bending moment is strictly determined by the compressive force and the eccentricity. The experimental resistance results are compared with those obtained from Eurocode's interaction equations according to method 1 and method 2. The test results will be used for strict validation of a shell numerical finite element model of tested subframe specimens and calibration of a novel analytical model of beam column backing resistance based on a generalized Ayrton-Perry formulation. The research had received funding from a grant for young researchers. A special acknowledgement go to the Structures Laboratory of the Rzeszów University of Technology to provide facilities and staff for carrying out the experimental work. So thank you for your attention.